So in the last video, we took a look at a somewhat more involved kinematics problem in one dimension. There was like a hammer falling from a roof, and there were several steps to the problem. And in part B, we had to use the result from part A. So in each part, we only really used one equation, but there was some information from the previous part that we had to use. It was still a very simple type of problem. In this video, we're going to be taking a look at a more complex problem where there are multiple different not parts of the problem, but steps to get the answer. So this is a pretty complex one-dimensional kinematics problem. I would say that the problems are harder to make. A pretty complex one-dimensional kinematics problem, it's difficult to make the problems harder than this. So if you can solve a problem like this, you can pretty much solve any one-dimensional kinematics problems. So the setup is this. A distracted driver is driving on the wrong side of the road. So here's the road, here's the distracted driver driving on the wrong side of the road, and over here there's a driver driving the correct way on the right side of the road. And let's see, distracted driver is driving on the wrong side of the road when he notices an oncoming vehicle moving towards him, this one. He quickly applies the brakes, causing his car to decelerate at 4.5 meters per second squared. So let's call this car 1 and this car 2. So A1 is equal to negative 4.5 meters per second squared. And from an initial speed of 20 meters per second, so initially going at 20 meters per second equals V01, meaning initial velocity of car 1. The other driver also applies the brakes 1.1 seconds later. So 1.1 seconds later, after driver 1 applies the brake, driver 2 applies his brakes, decelerating at 5 meters per second squared from an initial velocity of 23 meters per second. So V02 equals 23 meters per second, and A2 is equal to negative 5 meters per second squared. At the instant the distracted driver, car 1, applies the brakes, the front of each car is separated by 117 meters. And then the problem is going to ask us, is there a collision between the two cars? So we're only asked to find one piece of information. Is there a collision between the two cars? And what that means is that, so at the second that he begins decelerating, the distance between the front of the cars is 117 meters. At the moment that the distracted driver applies the brakes, the distance between the fronts of the cars is 117 meters. And this is let's call this delta x total. There are several different ways I'm sure you could approach this problem. I'm going to be going through one way, the first way that came to my mind. So what my thought process was, I will calculate the amount of time it takes each car to come to a complete stop, convert that into space, add them together, and see if it's less than this delta x total. If it is, there's no collision. If it's more, there is a collision. So translating that into physics, first we will find the amount of time it takes for car 1 to come to a complete stop. And the simplest equation we can use for that is this first kinematic equation. So for car 1, V final equals V initial plus a t, and that's going to be Final velocity we want is 0 meters per second equals 20 meters per second minus 4.5 meters per second squared times time. Let's rearrange this. This is going to be 20 divided by 4.5 is equal to 4.4 repeating seconds it takes the car 1 to stop. Okay, so this is how long it takes car 1 to stop. Now let's calculate the amount of time it takes car 2 to stop. We can use the same equation just for car 2. V final equals V initial plus AT is going to be 0 meters per second is equal to 23 meters per second minus 5 meters per second squared times time. This will be 23 divided by 5. Skipping some algebra steps. I hope you can see how I got that. 23 divided by 5 seconds is equal to 4.6 seconds, apparently. 4.6 seconds for car 2 to stop. Now, the important information that we got is car 2 doesn't begin applying the brakes until 1.1 seconds after car 1 begins applying them. So it travels some distance. Car 1 hits the brakes. Car 2 travels some distance at this velocity before applying the brakes. We need to calculate that distance. To calculate the distance, we can use equation 2, and during those 1.1 seconds, it's traveling at a constant velocity, meaning its acceleration is 0. So this term will go to 0. Still for car 2, we have xf equals xi plus vit plus 1/2 at squared. This is going to go to 0. Let's bring this over here and call this delta x gap, because there's a time gap between when car 1 applies the brakes and when car 2 applies the brakes. So I'll call it delta x gap, and that's just equal to vi2 times time. And this time is 1.1 seconds, and vi2 is 23 meters per second. 23 meters per second times 1.1 seconds is equal to 25.3 meters. 25.3 meters is delta x gap. So far we found that delta x gap is 25.3 meters. We found that T for car 1 is equal to 4.4 repeating seconds, and time it takes for car 2 to stop is equal to 4.6 seconds. Let's convert these times into space using, let's convert the times into space using this second equation. So first for car 1, I'll subtract x initial from both sides and just call it delta x1 for car 1 is equal to initial velocity is 20 meters per second times amount of time it takes for it to come to a stop is 4.4 repeating seconds minus 1/2 times 4.5 meters per second squared, again times 4.4 repeating seconds squared. And this is equal to 44.449 meters. Let's call it 44.45 meters. And now let's do it for car 2. Delta x2 is equal to 23 meters per second times 4.6 seconds minus 1/2 5 meters per second squared times 4.6 seconds squared, and that is equal to 52.9 meters. 52.9 meters. So now we have an amount of space here, an amount of space here, plus the amount of space it takes, the amount of space this car travels in the time it takes between this car applying the brakes and this car applying the brakes. Let's add them up. If it's greater than 117 meters, it means that the fronts of the cars were at the same location in space at some time, meaning there was a collision. Okay, so we found delta x car 1 is equal to 44.45 meters. Delta x car 2 is equal to 52.9 meters. And delta x gap is equal to 25.3 meters. Let's add them up. Okay, so let's add these up. They add up to, you can check this, 122.65 meters. And this is greater than 117 meters, meaning there is a collision. These accelerations or these decelerations are not strong enough to stop the cars before they collide. So there is a collision. Again, this is a pretty complex problem with two moving bodies and multiple steps using multiple equations to solve for various things. And then it takes a little bit of creativity to come up with a solution. I'm sure there are various other ways to solve this problem. This was just the first way that I thought about. And again, this is about as complex as a one-dimensional kinematics problem can get. So if you see the reasoning behind this, how to solve it, you feel like you could solve it, then you're good on one-dimensional kinematics problems. You can solve any one that comes your way. In the next video, I will be showing that these are actually space and velocity and acceleration are actually vectors. So not everything in the real world happens in one dimension. You can, believe it or not, an object can be traveling in X and Y at the same time, or in, a combination of X, Y, and Z. So in 3 dimensions, 3 spatial dimensions at the same time. So I will be showing how we can break these up if we allow the space and velocity and acceleration to be vectors. We can break them up into their respective components and solve some more complex problems, particularly projectile motion problems and things of that nature. So that'll be coming up in the next couple videos. Thank you for watching.